Hi everyone, I'm Gisele Bihina from CTICM in France, and I'm here today to present you the main results from a research work on partially or fully timber encased steel section, where the timber was used as a passive fire protection. This research work was conducted in the scope of MIBAPRO, which is a French national research project on composite structures made of bio-based materials in terms of fire protection and mechanical performance. The project involved 3 partners, including l'Institut Pascal à Clermont-Ferrand, l'UT Clermont-Auvergne à Montluçon, and CTICM near Paris. This research work consisted in 2 main parts. First, an experimental campaign carried out by Institut Pascal and UIT de Montluçon, and second, a finite element analysis conducted by CTICM. Regarding the experimental campaign, there were 9 standard fire tests on unloaded stocky steel profiles and timber molders or blocks. We even had hybrid steel timber specimens, which were all set in small furnaces. So you can see that we could have only a steel profile without any timber at all, or we could have timber molders or blocks without any steel at all. We could also have steel profiles with a partial encasement of timber. The steel profiles could be made of I-shaped section or T-shaped sections. The following table shows you the different characteristics of the different specimens. You can see that different timber species were used: Douglas fir, glue-laminated timber, pine, and you can also see that the fire exposure could be considered on 3 or 4 sides, depending on the specimens. We must also keep in mind that, unfortunately, the results from tests 3 and 4 were not reliable, so these results were not analyzed in the finite element simulation. Regarding this finite element simulation, well, actually, some assumptions were made in our model regarding first the symmetry and second the material properties. For the symmetry, as the geometry was symmetrical and we also had a symmetrical fire exposure, we considered that in case of 3-side exposure, only half of the cross sections could be modeled, and in case of 4-side fire exposure, only a quarter of the cross section could be modeled. The material properties were taken in accordance with Eurocodes, namely Eurocode 3 part 1.2 for steel and Eurocode 5 part 1.2 for timber. However, regarding the specific material that is timber, we also accounted for a proposal by Audebert in his PhD thesis more than a decade ago, which considers the vapor barrier effect induced by the steel profile in the specific heat of the timber. So here you have a picture of the tested specimen in test number 1 and a view of the cross-section that was modeled in our finite element analysis. As the specimen was exposed on 3 sides, we modeled a 70 millimeter thick concrete slab above the steel profile. For the timber molders, we consider specific modeling as there was a 3 millimeter thick layer at the interface with the steel profile, and the rest of the timber was modeled with different material properties, or these 2 parts were modeled using Eurocode 5 specific heat curve. That is, in some cases, we only consider the specific heat curve given in Eurocode 5 for the 2 parts, the green one and the purple one. In other cases, we considered a specific heat curve for the green part and another specific heat curve for the purple part. Actually, if we take a look at the plot of the specific heat curves of the material, you have in red that of steel, which was unchanged. And for timber, you have in blue the value given by Eurocode 5. You can see a peak value below 20,000. But when you consider Audebert proposal, at the interface you have a peak value of 100,000, and in the rest of the molder you have a peak value that is very low, that is much lower to that given in Eurocode 5. So different calculations were made considering these assumptions. Regarding test number 7, which was conducted only on timber blocks, we modeled in a single analysis different cross-sections of timber: glue laminated, fir, pine, and Douglas fir. Now, if we take a look at the results from our analysis, we first compare the sharing rates from the design values given in Eurocode 5 part 1.2 and from our calculation results. And we can see that if we consider the definition of the char line at the position of the 300 Celsius degrees isotherms, we have conservative results from our finite element analysis, as you can see on the left-hand side graph of the slide. And when it must be noted that this first comparison with the standard values was made based on the standard fire curve. So we had some calculations that were made using the nominal standard fire curve. And we also had calculations using the average fire curve measured during the fire test. We compared the sharing rate from our finite element analysis to the sharing rates from the experimental results. And again, we can see that our finite element model gives conservative results in terms of sharing rates. Now, if we take a look at the heating of the different parts of the specimens, for instance, if we consider test number 8, we can see that the results are not that conservative whether we use the specific heat curve from Eurocode 5 or from Audebert. But when we consider the specific heat curve from Audebert, we can have results that are very close to those obtained from the experimental campaign. For instance, if you consider thermocouple number 14, which is in green on the graph, you can see that the curves measured and calculated almost lie on top of each other. The same can be observed for thermocouple number 24, which is in yellow on the graph. So even though the results in terms of heating of timber are not conservative apparently, they can be quite close to that obtained from the fire tests. Now, if we consider the heating of the steel profile, we can see that we have conservative results from finite element analysis, regardless of the specific heat curve that is used in the finite element analysis. Actually, we can see that the dotted lines for a specific measurement point is always above the straight line that we can see. For instance, for thermocouple number 3, which is in blue, you have here the curve from the finite element analysis, and below it you have the curve from the experimental campaign. And again, like for timber molders, we can see that when we consider the specific heat curve given by Audebert in his PhD thesis, we get results that are quite close to that obtained from the test results. For instance, on thermocouple number 5, which is on the upper side of the upper flange of the steel profile, you can see that during the first 30 minutes, the curves do lie on top of each other. So now we have here a general comparison of the different results from our finite element analysis and from the experimental campaign. When we use the peak value from Eurocode 5 part 1.2, we have lots of safe-sided results, as you can see on the left-hand side of the slide. When you use the specific heat curve from Audebert, we still have some safe-sided results, but they are much closer to the results from the experimental campaign, which was already said in the previous slide. So the general conclusion is that our finite element model, based on the assumptions that were made, leads to conservative results, and the results can be even very close to those measured during the fire test, especially when you use Audebert proposal for the specific heat of the timber. And we can see that the temperature of the steel profiles are quite low in comparison in the case where they wouldn't be fire protected at all. Therefore, timber can be used as an alternative fire protection for low fire resistance rates, namely R15 or R13. Further work could consist in proposing more efficient encasement solutions that could actually be applied in practice in real projects in order to reach higher fire resistance rates, namely R60 or even more. Why not? So this could then lead to some fire protection that is bio-based and that is quite an alternative to the traditional and existing solutions. Intumescent coating, spray protection, plasterboard, or even concrete in some cases. So thank you for watching this presentation. And if you have any questions, I'm quite willing to answer to them as far as I can.